Hello, in this lecture we'll find out the length of line segment AE. In the drawing we have a rectangle, ABCD is a rectangle. Beside this rectangle we have those two semicircles. The radius of the big semicircle is 2 units. The radius of the small semicircle is 1 unit. In addition, we know that side AD of rectangle ABCD equals to 4 units in its length. And our mission is to find out the length of this line segment AE. So, first of all, we know that ABCD is a rectangle. And we know that all the angles inside the rectangle are right angles. So, this angle DAB, is a right angle. This angle ADC is also a right angle. Angle BCD is a right angle. And finally, this is angle ABC. This is also a right angle. In the next step, we will define the relevant points for this question with letters. We will define the center of the big semicircle. This point is point P. We will define the center of this semicircle. This point is point Q. We will define the touching point of those two semicircles with each other. This point is point S. We will define the point of tendency of tangent AE with this big semicircle. This point is point L. We will define the point of tendency of tangent AE with this small semicircle. This point is point G. In the next step, we will do a construction. That is to say, we will extend AE and side DC by straight line until they touch each other. And we will define the touching point. This point is point F. DC is one side of rectangle ABCD, therefore it is absolutely straight line. We extended the straight line DC by straight line, and the result is DF. When you extend the straight line by straight line, the result must be also a straight line. So DF is also a straight line. If we focus on the upper side of the straight line DF at point C here, the sum of the angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. Therefore, the sum of those two angles must be equal to 180 degrees, according to the rule that the sum of the angles in the upper side of the straight line DF must be equal to 180 degrees. So which angles we have in the upper side of DF at point C? We have this angle that is a right angle, plus this missing angle. In total, they must be equal to 180 degrees according to rule 3, the rule that I mentioned. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we define this angle angle F is alpha, and in the right triangle ECF, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus alpha. Likewise, in the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing angle must be equal to 90 degrees minus alpha. So I will explain why this angle must be equal to 90 degrees minus alpha, because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. In the next step, we will focus on the big semicircle. So PL is the radius of this big semicircle that is equals to 2 units in its length. Now we can implement here rule 1. So I'll repeat quickly on rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have tangent AB that is tangent to this circle at point M. And we also have the radius OM that is equals to half, so the radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle equals to 90 degrees according to this rule, rule 1. So we can actually implement rule 1 here in the big semicircle. We have the radius PL. The radius PL of this big semicircle is drawn to point L. This is the point of tendency of tangent AE with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees in its size according to rule 1. Likewise, we have in the big semicircle, the small semicircle, we have the radius QG that is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this again also equals to 90 degrees according to rule 1. So in the right triangle QGF, this angle equals to alpha, this angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus alpha, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the right triangle LPF, in this right triangle LPF, this angle equals to 90 degrees, this angle equals to alpha, therefore this missing angle, this missing third angle must be equal to 90 degrees minus alpha. In the next step, we'll prove that triangle LPF is similar to this triangle QGF. Okay, so we'll prove the triangle LPF is similar to this triangle, triangle ECF, to this triangle, triangle GQF. Okay, again, triangle LPF is similar to the right triangle GQF. So I'll write it down. So, triangle LPF is similar to this triangle QGF. So why those two triangles are similar to each other? First of all, those two angles they are both equal to 90 degrees, therefore they are equal to each other. So actually this is the angle PLF, in the right triangle LPF, and this equals to this angle, that is actually angle QGF, and the small triangle FGQ. Repeat again. If we found out that angle PLF in the big triangle LPF equals to angle QGF in the small triangle QGF, they are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both triangles. So you can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it is belongs to the big triangle LPF, it will be defined as angle LFP. And angle alpha equals to itself. So if we relate to this angle alpha as it is belongs to the small triangle GQF, it will be defined as angle GFQ. So repeat again. This equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle LPF. In the big right triangle LPF, and it is equals to this angle, that is actually angle GQF, in small right triangle GQF. Repeat again, I should found out that angle LPF in the big right triangle LPF equals to angle GQF in the small right triangle FGQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in this big triangle LPF are correspondingly equal to all the triangles in this small triangle GQF. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. I found out that the big right triangle LPF is similar, this is the sign of similar, to the right small triangle QGF according to angle similarity rule. And from the fact that the right triangle LPF is similar to the right triangle GQF, we derive that the following relationship exists between their sides. We derive that side LP in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. Because again, we derive the side P in the big triangle over side GQ in the small triangle equals to side PF in the big triangle over side QF in the small triangle. In the next step, we'll define the length of this line segment CF as X. So LP is the radius of this big semicircle that is equals to 2 units in its length over GQ. GQ is 1, it is the radius of the small circle, that is equals to 1 unit in its length, and it is equals to PF. What is the length of PF? First of all, PS is the radius of this big semicircle, and therefore it is equals to 2 units in its length. SQ is the radius of this small semicircle, that is equals to 1 unit in its length, and QC is also the radius of this small semicircle, and therefore it is equals to 1 unit in its length. And CF equals to X. So in total, PF in total equals to 2 plus 1 plus 1, that is 4, plus X. And again, in total PF equals to 4 plus X. PF equals to 4 plus X. And what is the value of QF? QF in total equals to 1 plus X. Again, QF in total equals to QC, that is 1, plus CF, that is X. So in total, QF equals to 1 plus X. So in conclusion, we found out that 2 over 1 equals to 4 plus X over 1 plus X. Here we multiply this equation, and we get that 2 times 1 plus X equals to 4 plus X. Here we'll open the brackets, and in this side of the equation we get that 2 times 1 is 2 plus 2x equals to 4 plus x. Here we subtract x from this equation, and we get that here 2 plus 2x minus x is x equals to 4. Here we subtract, okay, so 2 plus x equals to 4. Here we subtract 2 from this equation, and finally we get that x equals to 4 minus 2 is 2, so x equals to 2 units in its length. So if you found out that line segment CF that is equals to x is equals to 2 units. In the next step, we will prove that the small right triangle ECF, this small right triangle ECF, is similar to the big right triangle ADF. So I write it down. Repeat again. We will prove that the big right triangle ADF, the biggest right triangle in this drawing is ADF. Is similar to the smallest right triangle in this drawing, that is actually triangle ECF. So we will prove that the biggest right triangle in this drawing, that is ADF, is similar to the smallest right triangle in this drawing, that is ACF. Okay. So why the biggest right triangle is similar to the smallest right triangle in this drawing? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. Actually, this is angle ADF. in the biggest right triangle ADF, and this equals to this angle, that is actually angle ECF. In the smallest right triangle is this drawing ECF. Repeat again, I should found out that angle ADF, the biggest right angle, is equal to angle ECF in the smallest right angle in the drawing. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So can I note that angle alpha equals to itself? That's a common angle that belongs to both triangles. So if you relate to this angle alpha as it belongs to the big right triangle ADF, it will be defined as angle AFD. And angle alpha equals to itself. So if you relate to angle alpha as it belongs to the smallest right triangle ECF, it will be defined as angle EFC. Repeat again. Okay, found out that angle AFD, actually this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles, to the biggest right triangle AFD and the smallest right triangle in the drawing, that is ECF. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle DAF, in the big right triangle ADF, and it is equal to this angle, that is actually angle FEC, the small right triangle ECF. Again, if we found out that angle DAF in the big right triangle AFD equals to angle FEC, the small right triangle EFC, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we actually proved that all the triangles in the big right triangle ADF are correspondingly equal to all the triangles in this small right triangle ECF, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. We should find out that the big right triangle ADF is similar. Again, this is the sign of similar to the small right triangle ECF according to angle similarity rule. And from the fact that the biggest right triangle in the drawing is similar to the smallest right triangle in the drawing, we will derive that the following relationship exists between their sides. That side AD, the biggest right triangle ADF, over side EC in the small right triangle ECF equals to DF in the biggest right triangle ADF over CF in the small right triangle ECF. Repeat again, I should found out that A D in the big triangle over AC in the small triangle equals to DF in the big triangle over CF in the small triangle. What is the value of DF? First of all, PD is the radius of this big semicircle because P is the center of this big semicircle and D is the point of the semicircle itself. This is exactly the definition of a radius. Therefore, PD is the radius of this big semicircle. Therefore, it is equal to 2 units in its length. So, DF in total will be equal to 2 plus 2, that is 4, plus 1 plus 1, that is 6, plus 2, that is 8. So in total, DF equals to 8 units. Again, 2 plus 2 is 4, plus 1 is 5, plus 1 is 6, and 6 plus 2 is 8. So DF in total equals to 8 units in its length. Okay, DF equals to 8 units over CF. CF is 2, and it is equals to AD. AD is 3 according to what is given as the question, over EC. EC is the missing side, so we will leave it as it is. So we shall find out that 3 over EC equals to 8 over 2. 8 over 2 is 4. So in total we shall find out that 3 over EC equals to 4. Here we will multiply this equation by EC and then we will divide it by 4. And we get that EC equals to 3 quarters. EC equals to 3 quarters. This is side EC and this equals to 3 quarters, so 0.25. 0.25. So what is the length of the missing side BE? BE, first of all, we know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle ABCD, side AD equals to side BC. But AD is free, therefore BC is also free. So BC is free, EC is 0.25, and therefore BE will be equal to BC, that is free. Actually, 3 quarters is 0.75. EC equals to 3 quarters, that is 0.75. So BE equals to BC, that is 3, minus 0.75. 3 minus 0.75 equals to 2.25. So BE equals to 2.25. In rectangle ABCD, side DC equals to the opposite side AB. DC equals in total to 2 plus 2 plus 1 plus 1. 2 plus 2 is 4, plus 1 is 5, plus 1 is 6. So DC in total equals to 6 units in length, and the opposite sides of the rectangle are equal to each other. So DC equals to AB. DC is 6, therefore AB will be also equal to 6. Okay. So in the next step, I copy the right triangle ABE in a new page, and we will implement the Pythagoras theorem on this right triangle, triangle ABE. According to the Pythagoras theorem, in any right triangle, the score they are produced equals to the sum of the scores of the perpendiculars. side AB equals to 6 units in its length. Side B equals to 2.25, and the hypotenuse AE is the missing. AE is the line segment that we are looking for in this question. Actually, this is the right triangle ABE, this is the point from the original drawing. Again, AB equals to 6, B equals to 2.25. AE is the missing hypotenuse in this question. That is the line segment that we are looking for in this question. Here by PT is a relation from Pythagoras theorem. According to the Pythagoras theorem, AE squared, that is the square of the hypotenuse, equals to AB squared plus BE squared. So AE is the missing hypotenuse, therefore the limit as it is, so it is AE squared equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36, plus BE squared. BE is 2.25, therefore BE squared is 2.25. This equals to 5.062. So check it again. So this 2.25 square equals to find 5.0625. So in total, AE square equals to 36 plus 5.0625. 36 plus 5.0625 equals to 41.0625. So in conclusion, we found out that AE square equals to 41.0625. Here we take a root out of this equation, and finally we get that the missing line segment AE equals to the square root of 41.0625. That actually equals to 6.408 units. Repeat again, we actually found out that the length of line segment AE equals to 6.408 units. And that is the answer to the question. So in the next step, I'll summarize the lecture. In this lecture, we found out the length of this line segment AE. And again, we found out the length of this line segment AE. In the drawing, we have rectangle ABCD. Inside this rectangle ABCD, we have those two semicircles. The radius of this big semicircle is 2 units. The radius of this small semicircle is 1 unit. In addition, you know that side AD of this rectangle ABCD is equal to 3 units in its length. Again, our mission is to find out the length of this line segment AE. So, in the first step, we actually know that all the angles inside any rectangle are right angles. So, those 4 angles, they're all right angles. In the next step, we defined the relevant points to this question with letters. We define the center of this big semicircle, this point is point P. We define the center of this small semicircle, this point is point Q. We define the touching point between the big semicircle and this small semicircle, this point is point S. We define the point of tendency of tangent AE with this big semicircle, this point is point L. We define the point of tendency of tangent AE with this small semicircle, this point is point G. In the next step, we did a construction, that is to say, we extended line segment AE and side DC of this rectangle ABCD by a straight line until they touch each other. We define their touching point, this point is point F. Then, actually, note that DC is one side of rectangle ABCD, therefore it is absolutely a straight line. Then, when you extended the straight line DC by straight line, the result is DF. When you extend the straight line by straight line, the result must be a straight line. Therefore, DF is a straight line. So if you focus on the upper side of the straight line DF at point C, here the sum of the angles must be equal to 180 degrees according to rule 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So the sum of the angles in the upper side of DF at point C must be equal to 180 degrees according to rule 3. So which angles we have at the upper side of DF at point C? We have this angle that is the right angle plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we defined this angle EFC as alpha. So in the right small triangle EFC, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees. And 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the big right triangle ADF. In the big right triangle ADF, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this further angle must be equal to 90 degrees minus alpha according to the sum rule, that the sum of the angles in any triangle is equal to 180 degrees. PL is the radius of this big semicircle that is equal to 2 units in its length. Here we can implement rule 1 because we have the radius PL that is on to point L, that is the point of tendency of tangent AE with this big semicircle. And whenever you have radius that is on to the point of tendency, then tangent AE will be perpendicular to the radius LP. If AE is perpendicular to LP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. Likewise, we have here the radius QG of the small semicircle. This small semicircle is drawn to point G, that is the point of tendency of tangent AE with this small semicircle. And whenever your radius is drawn to the point of tendency, then tangent AE will be perpendicular to the radius GQ. If AE is perpendicular to GQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the right triangle LPF, this angle equals to 90 degrees, this angle equals to alpha, therefore this further angle must be equal to 90 degrees minus alpha. Likewise, in the small right triangle GQF, this angle equals to 90 degrees, this angle equals to alpha, therefore this further angle must be equal to 90 degrees minus alpha. In the next step, we proved that the big right triangle LPF is similar to this small right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So I should prove that all the three angles of the big right triangle LPF are correspondingly equal to all the three angles of the right triangle GQF. Therefore, those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side LP in the big triangle or side GQ in the small triangle equals to side PF in the big triangle or side QF in the small triangle. Repeat again. We derive that side LP in the big triangle or side GQ in the small triangle equals to side PF in the big triangle or side QF in the small triangle. LP is the radius of the big semicircle, that is 2, over GQ. GQ is the radius of this small semicircle, that is 1, and it is equals to PF. PF, we actually define the length of this line segment CF as X. PS is the radius of this big semicircle, that is 2. SQ is the radius of this small semicircle, that is 1. QC is also the radius of this semicircle, that is 1. So in total, PF in total equals to 2 plus 1 plus 1, that is 4 plus X. Again, PF in total equals to 2 plus 1 plus 1, that is 4 plus X. So PF in total equals to 4 plus X. So here, PF equals to 4 plus X over over QF. QF in total equals to 1 plus X. Again, QF in total equals to 1 plus X. Here, QF equals to 1 plus X. So the conclusion found out that 2 over 1 equals to 4 plus X over 1 plus X. Here we cross multiply this equation and finally found out that 2 times 1 plus X equals to 4 plus X. Here we open the brackets on this side of the equation and we found out that 2 times 1 is 2 plus 2x equals to 4 plus X. Here we subtracted X from this equation and finally found out that 2x minus X is X. So here in this side of the equation we have 2 plus X equals to 4. 2 plus X equals to 4. Here we subtracted 2 from this equation and finally found out that X equals to 2. So this line segment CF that equals to X equals to 2 units. So in the next step we proved that the smallest triangle in this drawing, that is triangle ECF, the smallest right triangle ECF is similar to the biggest right triangle in this drawing, that is triangle ADF. Because again, we proved that the biggest right triangle ADF is similar to the smallest right triangle, this right triangle ECF. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So you can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the triangles in the biggest right triangle ADF are correspondingly equal to all the triangles in the smallest right triangle ECF. And therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AD in the big right triangle over side EC in the small right triangle equals to side DF in the big triangle over side CF in the small triangle. Okay, again, we derive that side AD in the big right triangle over side DC in the small right triangle equals to side DF in the big right triangle over side CF in the small right triangle. AD is free according to what is given as the question. Over EC, EC is the missing side, therefore we leave it as it is. Equals to DF. DF in total equals to 2 plus 2, that is 4, plus 1 plus 1, that is in total 6, plus 2, that is 8. So DF in total is 8 over CF. CF is 2. So in conclusion, we should find out that 3 over AC equals to 8 over 2. 8 over 2 is 4. So in conclusion, we should find out that 3 over EC equals to 4. We multiply this equation by EC and then we divide it by 4 and finally found out that the missing 970 EC equals to 3/4. So actually this is the missing 970 EC, that equals to 3/4, so 0.75. So what is the left of the missing side BE? BE will be equal to BC minus BE. BE equals to BC minus EC. Again, BE equals to BC minus EC. So BE equals to BC, that is 3, according to all the opposite sides of an rectangle are equal to each other. AB equals to 3, therefore BC will be equal to 3 also. So BC is 3 minus EC, that is 0.75. 3 minus 0.75 is 2.25. So we actually found out that the missing side BE equals to 2.25. And we have the rule that the opposite sides of a rectangle are equal to each other. So in rectangle ABCD, side AB must be equal to the opposite side DC. What is the length of DC? DC in total equals to 2 plus 2, that is 4, plus 1 plus 1, that is in total 6. So DC equals to 6, therefore the opposite side AB must be also equal to 6. In the next step, we copied this right triangle ABE in a new page, and we implemented the Pythagoras theorem in this right triangle, triangle ABE. So actually, this is right triangle ABE, that is coming from the original drawing. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle ABE is AE, therefore the square of the hypotenuse is AE square, and it must be equal to AB square plus BE square. So AE is the missing side of limited cities, so AE square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BE square. BE is 2.25, therefore BE square is 2.25 squared, that is 5.0625. So in total, we found out that AE square equals to 36 plus 5.0625, 36 plus 5.0625 equals to 41.0625. So in conclusion, we found out that AE square equals to 41.0625. Here we took out of this equation and finally found out that the missing 97 AE, the 97 that we are looking for in this question, equals to the square root of 41.0625, that is actually equals to 6.408 units. Again, the length of this 97 AE is equals to 6.408 units. Okay, thank you very much.